Hello folks, in this video we're going to talk about the concept of force and Newton's second law. You'll remember his first law was the law of inertia. A body at rest tends to stay at rest. A body in motion tends to stay at motion at constant velocity. So forces and the second law, Newton's second law, named for Sir Isaac Newton, who developed the laws of motion that we now consider to be central to our classical explanation for the world. He also, and that's the first, second, and third laws. We've talked about the first law. We're talking about the second law in this video. The third law we'll discuss in the next video. Also the law of gravity, gravitational attraction between bodies of mass. He discovered the theory of that and developed the equations that explain those interactions. Also calculus. In order to do a lot of the calculations that Newton did to deal with the laws of the physical world, he needed to develop new math, and that new math was calculus that we all know and love right now. Leibniz was someone who developed calculus separately in a different way. The particular symbolism that Leibniz used was different from Newton, but it was calculus nonetheless. And you can find information about both Leibniz and Sir Isaac Newton on the web. There are links on this slide that go to their Wikipedia biographical descriptions. What Newton developed, and it's much more than just the laws of motion, laws of gravity that I've indicated here, is what we refer to as classical mechanics, which pretty much held sway as our description of the physical world through the end of the 19th century. Beginning of the 20th century, when there were a few cracks that were developed in those theories, because they didn't explain everything. They did a pretty good job, and we still use classical mechanics to do a lot of calculations, trajectories of planets, and celestial bodies, for example. So we still use classical mechanics, but it's not a complete description of reality. And beginning of the 20th century, Albert Einstein, of course, was influential in the development of new physics, including the theory of relativity, and of course quantum mechanics as well, which describes the behavior of atoms and molecules and subatomic particles, etc. So Isaac Newton was certainly one of the most influential scientists ever, and we certainly owe a great deal to him in terms of our abilities to predict and describe the physical world. So let's just talk about, basically what we're going to be talking about in this video is we're first going to introduce the concept of force. And describe what that means. We'll talk about the different types of forces that exist in nature that are really important for understanding our world. We'll talk about unbalanced forces and how that affects the trajectories of particles, which will lead us then to a description of Newton's second law and the mathematical expression for that, and then also the law of gravity. We'll talk about a few problems and calculations along the way. Some of these calculations will just be referred to in this video and will be described and worked through in detail in separate supplementary videos. So you'll need to stay tuned for that because I know you're interested. Okay, so what's going on here? All right, so first of all, when we talk about force, what do we mean by the force? Well, it's not this. And of course, as I record this video, it is actually just past May 4th. So if you're Star Wars fans, you know it's the day that we talk about. May the Force be with you. All right. But the force that's described in Star Wars is not a force that actually exists. And we can certainly talk more about that if you like, but it doesn't fit in with the fundamental forces of the universe as we know them. So what is a force? When we talk about forces, we're talking about something that causes a change in motion. Remember, the first law said that a body will remain at rest or a body will stay in motion unless some force is applied to it. The force causes a body at rest to move. A body in motion will actually continue at a constant velocity unless a force is applied. A force could be applied to stop the body from moving. It could be applied to make it move faster. It could be applied to make it change direction. So remember that velocity has direction as well as magnitude. So a change in direction, even at a constant speed, a change in direction can only be induced by a force. So that's something that we talk about. A force is something that causes a change in motion. Okay. All right, so the fundamental forces of nature as we know them, there is something called electroweak force, and frequently you will hear that there are four fundamental forces of nature, but I'm going to describe three of them because current theories, what's called the Standard Model, actually shows that two of the forces that were once thought to be separate, the electromagnetic force, which is the force of electricity and magnetism, and they actually go together. Electricity and magnetism are very closely related, and one can induce the other. That's how things like generators work, for example. We'll talk more about that in future videos. But electromagnetism, that interaction is a type of force. It's responsible for what holds electrons and nuclei together in atoms. It's the interaction between atoms and that leads to molecules. That electromagnetic force is actually a very, very important force when we talk about a lot of very important interactions in a lot of chemistry, for example. The electromagnetic force is the one that's the most important there. There's also something called the weak nuclear force, and the two of those actually were united some years ago in the Standard Model to create overall what we refer to as the electroweak force. So that actually, the two of those, which are sometimes listed as separate forces, actually constitute one force, which is called the electroweak force. And then, of course, there's the force of gravity, the gravitational force. We know that is something that is quite important, obviously. We feel gravity all the time. And there's something called the strong nuclear force, and the strong nuclear force is what holds nuclei together. The protons and neutrons in the nucleus of an atom are held together with what's called the strong nuclear force. So again, just to summarize, the electroweak force is the interaction between charged particles, and magnetism is the magnetic interactions also are united in what's called the electromagnetic force. It's responsible for molecules. It's responsible for holding matter together. That's the electromagnetic force. A weak nuclear force is a force that's related to radioactive decay, and that's really all we'll say about that. The gravitational force, of course, is an attraction between bodies of mass. And the strong nuclear force is the attraction between particles within the atomic nuclei, neutrons and protons, and that holds the nucleus together. It's actually also responsible for, if we want to get into a little bit of nitty-gritty here, the electromagnetic force is the force of chemistry, and so typical weapons, explosive devices like TNT and things like that, that energy comes from the electromagnetic force. The strong nuclear force is what is responsible for the energy associated with nuclear devices. So that's those are there are three main forces, and again, the electroweak force is actually a combination of these two forces. So those are the fundamental forces of nature. So everything that we're talking about can be described in terms of these forces. All right, so when you have multiple forces interacting on a body, the forces, because forces can change the direction of motion, forces also have direction. So like velocity, force has direction associated with it. And if all the forces on a body are balanced, that means that the forces are such that they cancel each other out. So for example, you could think about having a force moving in this direction, right, and a force moving in the opposite direction. All right, and if they're the same magnitude and they exactly oppose each other, they cancel each other out, and that's what we refer to as a balanced force. All right, and you can have multiple forces. You can think of something like this. Again, those forces will cancel each other out in a way that's balanced. And when the forces on a body are balanced, no change in motion will occur. In order for there to be a change in motion, there has to be unbalanced forces occurring. All right. So these unbalanced forces are responsible for change in motion. So this is a little video here that actually shows that. Here, I want to run that back. Here, I'm going to pause for a second so I can run this backwards. Okay, so let's run that video again and watch very carefully the breakdown here. Watch the pitch. This is a video that actually shows 3 different types of pitches coming from the same pitcher. So that's what you're seeing when you see that. So I'm going to back this up again. We're going to watch this one more time. So the 3 different pitches, and you can see that they end up in different locations. So we've got a pitch that ends up here, okay, and that 100 means that it was going 100 miles per hour. That's pretty darn fast. There's one pitch that ends up down here at 88 miles per hour, and there's one pitch that ends up here at 89 miles per hour. So this is something, you know, I've talked about baseball in past videos. What we have is a situation that shows how a pitcher can change up speeds and change up the direction of the ball based on different factors that the pitcher might use to fool the hitter, and that's the whole plan. So I'm going to back this up a second, and just bear with me here, and watch again the trajectories of the 3, and then on the next slide we're going to show a balance. So watch the 3, and you can see one curls off to the left, one curves off to the right, and one more or less goes straight through that. The 100 mile per hour kind of goes straight. The 88 we see going down here, curving to the left. This one curves to the right, where they all essentially start from the same place. All right, so that's an example of differences in unbalanced forces. And I want you to think about the nature of the forces involved here. This will be a separate question that we ask in a discussion forum to kind of describe the different forces, and not what causes them, but actually just to describe the directions of the different forces that might be affecting how the ball, for example, how does this ball, what would be the direction of the unbalanced forces that would cause this ball to go down and to the left? What about this ball going down and to the right, and this one essentially going straight? So we essentially have on this one, the ball is going straight because it is going from the pitcher to home plate, but it's going down and to the left. Here's one that's essentially going straight. It's coming down a tiny bit if you watch it carefully, and this one is down and to the right. All right, so what are the nature of the unbalanced forces? But again, this is an example of unbalanced forces causing the ball to move in different directions depending on the forces involved. Okay, so here on this slide, what we're going to do is go through, and I'm going to essentially make myself a little smaller here. These are just freeze frames. That's not going to let me do that. I thought it would, but it won't. All right, here's freeze frames that show this, that here's the pitch just after it's being leave the pitcher's arm here. You can see that pitch there. They haven't split off yet. All right, the next one shows that they're starting to split. So here's one that's going to the left. There's one that's going straight. Here's one that's going to the right. The next one, you can see the separation increasing as you're looking at, you know, these different pitches here. Okay, continuing. You can now see the much greater separation in this one. Boom, boom, boom. And again, you're just seeing this progression as we go through it. So again, unbalanced forces. So the pitcher is putting different spins on the ball that would cause it to go in these different directions. The one that's going straight, that kind of reaches right here at the end, is what we call a fastball, and it's just going essentially boom. Then we've got one that's curving down to the left, as I mentioned before, curving down to the right. Okay, so how are those forces changing, right? So, do you have a force going down? Do you have forces pushing it to the right? Do you have forces pushing it to the left? Those would represent the directions of forces that are used that cause the motion to go in different directions. Again, this is an example of unbalanced forces. All right, so that's unbalanced force. So we have force now, but let's move on to the second law because we don't have a quantitative measure of force, and that's where Newton's second law comes into play. We know that the changes in motion that are induced by force, change in velocity, so speed and direction is what we're talking about with regard to force. So that's clearly important. Velocity is clearly important, and changes in velocity are clearly important. So if we're talking about changes in velocity, you may remember that change in velocity corresponds to acceleration, right? That's a direct connection when we talk about this. Change in velocity means acceleration. All right, but we also should expect that mass plays a role in force because it just makes sense from your own perspective that the more massive an object, the more force has to be applied to change its direction. So when we talk about the quantitative definition of force, we got to include both mass and acceleration, and of course this leads to this equation, which you may already have heard of. Force is equal to mass times acceleration. This is Newton's second law. And we would write it simply F equals m for mass times a for acceleration. That's the second law of Newton's second law, not the second law of thermodynamics. That's something we'll talk about later, but it's Newton's second law. All right, so what about units? What do we know? What are the units of force? Because we talked about units in previous videos, and we know what units of mass would be. We know what units of velocity are. We know what units of acceleration would be. So when we talk about acceleration, so let's just talk about that just to refresh our memories, and certainly we dealt with this in previous videos, including calculations. So let's think about acceleration. We know that acceleration represents a change in velocity over time. All right, well, velocity has units in our metric system, and the SI units, or sometimes called the MKS units, as we talked about, in meters per second. And time has units of seconds. And so that means when we put them together that acceleration is going to be meters per second squared. If you heard that little groan, that was my dog who's complaining because I'm not paying attention to him and he's just lying down on the floor. So meters per second squared. That seems odd, but those are the units of acceleration. Again, that comes from the fact that we've got change in velocity. Velocity has units in meters per second over time, which is seconds. So that becomes meters divided by seconds times seconds, which is meters per second squared. Those are the units of acceleration. All right, so, and then we're going to combine that because, again, remember what we're talking about here. Force is equal to mass times acceleration. So acceleration has units of meters per second squared. What about mass? Well, mass has units of kilograms. All right, so we're going to put all that together because we're multiplying kilograms, all right, times meters per second squared. So the units are kilogram meters per second squared. Now that's odd, right? You don't kilogram meters per second squared every time you're dealing with force. Do you want to call it kilogram meters per second squared? No. So what we're going to do is we're going to invent a new unit. It's still based on the three basic units in our system are kilograms, meters, and seconds. But when we combine them in this way, we're creating, for force, we're creating a new unit, and we're calling that the Newton. Imagine that, named after the man himself, right? And we're just saying 1 Newton, which we represent by the symbol N, is equal to 1 kilogram meter per second squared. All right. So in the metric system, in our SI system of units, the units for force are newtons. All right. So keep that in mind. When we talk about the imperial units, the units that are used in the U.S., pounds represents a unit of force, but the metric unit that we're using is going to be what's called the newton. All right, so let's talk about a simple problem here. If I've got a car, how much force is required to accelerate a car from 0 to 60 miles per hour in 8 seconds? Well, we've already talked about how to calculate acceleration for this system. All right, so we're going to go ahead and do this here, if you'll bear with me for a few minutes. And so we know that we can calculate acceleration by looking at our change in velocity. And the change in velocity is 60 miles per hour. I'm just going to use mph for miles per hour, divided by the time of 8 seconds. All right, so that's going to be our acceleration. What else do we need for force? Well, we need mass. So I haven't given you any specific information about mass here, but we can just basically look up the typical mass of an automobile, car of some type, online, and that's what we'll use for that. So typically, we might be talking about something that's maybe on the order of 1,600 kilograms or less. All right, and that does clearly depend on the size of the vehicle. So I'm going to pause here for a second, and we're going to bring in our favorite Wolfram Alpha to work through this calculation, including the unit conversion. Okay, so we brought Wolfram Alpha into the picture. So let's calculate acceleration first. All right, and if you'll recall, and let me just pull this out just to remind you that we're talking about 60 miles per hour change in speed and velocity over a period of 8 seconds. All right, so okay. And so here are the various units that we can use for this. And again, let's just go ahead and go right to the metric system units, because that's what we're going to use. In order to get newtons for our force, we're going to want it in metric system. So we might as well do it now. So I'm going to go ahead and select the metric system here, 3.353 meters per second squared. I'm going to click on that because that allows it to go right up here into my Wolfram entry bar. And then our mass is 1,600 kilograms. And again, it's going to vary from car to car, but I actually chose 1,600 kilograms because that's roughly the mass of a Honda CR-V, which is the car that I recently purchased, hybrid version. And so we're just going to go ahead and multiply that by 1,600 kilograms. And here we go. All right. So there we have it down here in newtons. This would be kilonewtons, as you can see, which is 1,000. So in terms of newtons, it's 5,365 newtons. So let's just go ahead and write that down. That's how much force is required to do that. Now, when we talk about that, that means that, in order to go from 0 to 65 in that period of time, you need the force to do that, which also means you need the energy associated with the force. And energy is what we're going to be talking about in the not too distant future and looking at how that is. But within a typical automobile, a combustion engine, that energy is provided by the combustion of gasoline. Certainly in electric cars, the acceleration and the force required to accelerate the car results from electrical power generated by a battery. So that's how we calculate force. Okay. All right, so this video has gone on long enough. I'm sure you'll agree. So I'm going to stop here and go ahead, take a break, grab something to eat, grab a snack, and we will continue with this in another video soon. So stay tuned.